Hi, I'm Matt Walker, and we're talking about tidal heating and ice shells today. And I'm going to mess with the eccentricity, and we're going to see how different forcing models work. Great, so this is my email. Please email me. I would love to talk to you. We're looking at Europa today, but you could do this on Enceladus or any other, and here's a bunch of questions we're going to ask. We're using a 1D heat flow model, so we're going to have, and it's all conductive, so any divergence in flux or heat source or any imbalance between the two will cause the temperature to change. And we start simple with no heat source and an equilibrium. So you can solve this differential equation and you get this function, and we plot it here. So that's just a 25-kilometer shell shown. And here's what it looks like if you were to stick an ice shell under it. This is the base up here. Here's the surface. So I'm going to show lots of plots with this body radius axis so you can imagine that shell under there. The gradient of this temperature profile tells you about the heat flux. So different shell thicknesses will have different heat flux requirements at the shell base and at the surface. So if you plot them all out here, you see that if you wanted 10 milliwatts per meter squared at the shell base, you'd need like a 55-kilometer shell to get that. So it's pretty thick. So that's without a source. And there is a source. So when you use a source, there'll be a huge difference, and that's what this talks about. So let's get into it. So I'm going to use 3 different eccentricity models. Like I said, we got this constant eccentricity, and I'll look at a bunch of different values up to 0.02. There's this long period eccentricity model from Hussman Spohn. Really good, so we're going to try and emulate the eccentricity from that. And then there's this JPL Horizons eccentricity output that the results aren't great, but I'll show you what I did anyway, and then maybe someone can help me figure out what I messed up. Cool. Anytime you see anything about tidal heating, you're probably going to see this equation. And this has this K2 love number in here, which wraps up everything about the body, and this eccentricity squared. So that's the forcing. Now this thing is globally integrated, which means it's in watts, right? And it's integrated globally, so you can't tell where this heat is generated. And it's also a very, very simple tide to come up with this equation. So I'm doing something different. I'm doing the volumetric heat rate. And so this is watts per meter cubed. And it depends on the strain rate, the rigidity, so the rheology, and then the forcing frequency. So we're going to know where the heat's generated, and we can do complicated tides with this. If you want details about how the strain rate works, either email me or look in the Sabadini-Vermeersen book, really good book. I use a Maxwell rheology for the ice. So the important bit here is that heat, this blue thing, peaks at about 246. So that's not the melting temperature. It's a little bit colder than the melting temperature, which is in the ice near the base, but not quite the base, and that's important. And complicated tides have many frequencies, so you sum this thing up over every frequency. I'm not going to go into too many details about how I calculate the tide, but it's a pretty standard tide, and we use spin and orbit parameters, and I'm going to turn off the obliquity and make it a synchronous rotator. And I should point out it's expanded to first order in eccentricity so that we can handle the true anomaly. And then when you're done, it's a nice simple sum of all these coefficients and complex exponentials with a frequency in there, so it looks like a Fourier series, and you get frequencies and coefficients. The spectral power is what's important though. So this tidal heating is proportional to this bit. And that's what I'm going to use here. So spectral power. And you see it's also proportional to E squared. Cool. Oh, I put numbers on it too. Great. So you can see the relative magnitudes of these things. Some units. Great. So let's put a source on this thing now. So if this was what goes on with no source, so we stick that source on there, and when we do, you get this enhancement of temperature at the base, right? It pulls this temperature profile up, and this happens because you've got this heat generated in the body near the shell base, not quite at, but near the shell base. So you'd miss that if you didn't have these radially resolved tidal heat models, so super important already. Great. So because that temperature profile changes, so does the heat flux. You can see it, makes the profile less steep at the base, so less heat flux, but steepens it at the surface. It brings the heat flux up a little at the surface. So we can look at all different thicknesses of shells, right? So this is the 25-kilometer shell. that we looked at. A thin shell it makes very little tidal heating, right? It barely does anything here, and you've still got these really high basal heat fluxes. Go a little thicker, back to our 25. If you want to see what melt looks, here's what melt looks like, right? So we've melted a little off the top, and we've got this negative heat flux. That's not real. I'm just showing you what happens. I don't really model the melt. But there is a maximum shell that does not melt, and here it is. This is a 35.5 kilometer shell, and you've got really low basal heat flux. You can trace this to here, kind of, and then also a higher surface heat flux. Trace that to here. The relative width tells you something about how active the tide is there. So there's a huge difference. The tidal heating, just the tidal heating at a constant eccentricity model, is pulling the basal heat flux requirements way down. So this is comparing to the no source model. We're pulling that basal heat flux way down and not really doing much to the surface heat flux. Cool. Oh, and I also have this little range of plausible to possible shell thicknesses. So I'm saying this one is 26.5 kilometers, gets you that 10 milliwatts, up to the maximum 35.5. So at this eccentricity, that's the only range of shells that I think you're going to find. And I just said that, and now here's a cool little bar on it. Great. So we're going to check a different eccentricity model. We're going to use this very long period Husband-Spohn eccentricity model. So we get these big spikes, right? And I'm going to look at them two different ways. We're going to have broad peaks. So this is the function I'm modeling eccentricity with and some parameters. We're going to have broad peaks when I use a power of 2 on this thing, and sharper spikes when you use a power of 4 on this thing. What does it do? It splits the tide up. You get some spectral splitting of the tide, and you get even more splitting when you pick a power equals 4. So here's a thin shell with that eccentricity model, and you see with the thin shell what we're going to get is high heat flux, as we've seen before. So that's no problem. Not a whole lot of tidal heating. The thing's so thin you're not really doing much to it. But as we look at a little bit thicker shells, we see here's the tide doing its thing now. You're driving down that basal heat flux, and there is a maximum. This 17.5 kilometer shell is the maximum shell thickness that you're going to find for this eccentricity model. And I don't think it's that far off to say that. So when I say maximum, it's a maximum shell thickness on average over 280 million year eccentricity cycle. So that's a long period average, and the real solution is probably going to oscillate around that. Great. Oh yeah, and then also I put this 10 milliwatt grid line here just to see that the plausible range of shell thicknesses with this model is only 15.5 to 17.5, so that's pretty narrow. And I'm going to just compare it to the average eccentricity. If I pick that long period eccentricity model from Husband-Spohn, get its average, it's pretty big. E equals 0.017. So I'm just going to compare the average, and you see it does shift this a little bit. So now we've got 16.5 to 19 kilometers thick. What I'm trying to say here is if you use the constant eccentricity model, you lose heat. You need to deal with the oscillatory model because there's more spectral power in that tide. So you're getting more heat. So just picking a constant eccentricity misses that. So already I'm thinking this is cool stuff. I did the P equals 4 one too, so the more spiky ones, and you get similar behavior. The ranges are slightly different, and if you're interested, it's like 17 to 20 kilometers here. Great, and I compared it again to the constant model. So I did some stuff with horizons as well, and I took the thing, I did a Fourier series on it, I pulled it at 1-day resolution, Fourier series, picked the top 10 pieces, looked at the tide, and then fed it into my model, and I messed something up. There's something I messed up because I'm getting way less heat out of this thing, so maybe I coded it wrong, or maybe I chopped out all the spectral power by only picking the top 10, but whatever I did, something's wrong. So just ignore the horizon stuff, I guess. But anyway, it's time to summarize. So I just want to show you what this thing does because it's really cool. Imagine those fingers are the forcing, and we're going to just strip this thing open. Great. So I'm going to just spam you my conclusions. And there they are. and I'm going to say thanks. All right, thank you very much.